Energetics 3, Hess's law. Essential ideas. In chemical transformations, energy can neither be created nor destroyed. This is the first law of thermodynamics. Nature science. The hypothesis. Based on the conservation of energy and atomic theory, scientists can test the hypothesis that if the same products are formed from the same initial reactants, then the energy change should be the same regardless of the number of steps. First, let's have a word about words. Enthalpy change is the same thing as enthalpy of reaction, which is the same thing as delta H. The enthalpy of combustion, we can see here an example of methane with oxygen giving us carbon dioxide and water. The enthalpy of combustion is written with a little c at the bottom right hand side of the capital H. The enthalpy of solution has a little sol written there, and you can see enthalpy of solution describes a salt dissolving into water. We've gone from the solid to the aqueous form. You could also write it, you could also write the ions separately here if you so wished. Enthalpy of neutralization, write a little neut at the bottom right hand side. And the enthalpy of neutralization is the enthalpy change when an acid and a base gives a salt and water. What about this one? Liquid water going to gaseous water. Well, that is the enthalpy of vaporization. Next, what would be the enthalpy of solution of ammonium sulfate? That's right. It's the ammonium cation and the sulfate anion in aqueous solution coming from the solid. What's this one? We've got calcium chloride with water giving us the hydrated form of calcium chloride, and that's right, it is the enthalpy of hydration. And finally, another one for enthalpy of neutralization. We've got some sulfuric acid reacting with potassium hydroxide, the base, giving us the potassium sulfate salt and water. Let's have a think about energy changes, and we'll just think about potential energy here. At each level in the school, you've got a different amount of potential energy. If you're very high up, you've got more potential energy than if you're very low down. Let's start in the level 3 classroom. If we walk up to the Maple Cafe, it takes us a certain number of floors. It's 3 floors up, isn't it? It's on the 6th floor. We could also get the Maple Cafe though by going up to the principal's office and then back down to the Maple Cafe. We'd be going 6 up and 3 down. Of course, 6 up and 3 down is the same as 3. Alternatively, we could go down to the math floor, the 2nd floor, and then go up to the Maple Cafe. And that'd be -1. +4, which again would give us 3. So no matter which route you take, the sum of the change is always +3. So many reactions can follow different paths. The enthalpy change for a reaction is the same no matter what path you take to convert the reactants into the products. And this is Hess's law. A more formal statement of Hess's law is as follows. Whenever a reaction may be expressed as a series of a number of small steps, then the enthalpy change for that reaction is the sum of the enthalpy changes of the small steps. And that'll come to make sense when we do some examples. If you look at this diagram here, if you have reactants A, and after reaction you get product D, the enthalpy change is delta H1. Okay? What we're trying to understand here is that if you do a different reaction and you change reactants A into products B, and then change B into C, and then change C into D, then the overall change here is going to be the same as this change here. The total enthalpy change of this route is going to be the same as this route. Oops. Delta H1 will equal delta H2 plus delta H3 plus delta H4, the indirect path. So path 1 will equal path 2 with regards to enthalpy change. Delta H1 equals delta H2 plus delta H3 plus delta H4. This diagram is called an enthalpy or energy cycle. An enthalpy cycle. Let's have a look at some enthalpy cycle examples. Example 1. Enthalpy of neutralization of solid sodium hydroxide. You've got sodium hydroxide reacting with hydrochloric acid to give sodium chloride and water, aqueous sodium chloride and water. The direct path would be a reaction with the solid sodium hydroxide and the hydrochloric acid, and that enthalpy change would be enthalpy change H1. The indirect path here is the sodium hydroxide dissolves first in water to give aqueous sodium hydroxide. Then the aqueous sodium hydroxide reacts with aqueous HCl to give us the sodium chloride and water. Okay, and as we know, this path here is going to equal the sum of this path, H2, and delta H3. So delta H1 will equal delta H2 plus delta H3. And so delta H1 is going to equal minus 43 kilojoules per mole plus minus 57 kilojoules per mole to give us minus 100 kilojoules per mole. So we've calculated the enthalpy change of this here using known enthalpy changes of these two other reactions. Enthalpy cycle example 2. Enthalpy of hydration of an anhydrous salt. We've got potassium sulfate and water giving us the hydrated potassium sulfate. The change here would be delta H1. This is the direct route. Indirect route, we can dissolve the copper sulfate, and the enthalpy of solution, which would be known for copper sulfate, gives us the copper ion and sulfate ion. This indirect route here to the copper ion and sulfate ion will have the same enthalpy change as delta H2. So if we add delta H1 to delta H3, we've gone from here to here. The direct route, this one; indirect route, this one. So delta H2 will equal delta H1 plus delta H3. You can rearrange that, and then we can find delta H1. It will be delta H2 minus delta H3. Why are we bothering with all this? Well, Hess's law provides a way to calculate the enthalpy change for a chemical reaction when it is not possible to reliably or safely carry out the reaction to find an experimentally determined delta H value. The algebraic approach to Hess's law. Some background. Adding equations. You can add chemical equations together to give a new target equation. Chemical species that appear on both sides of the equation cancel each other out. So let's look at example 1. We've got hydrogen gas plus oxygen gas giving us gaseous water. And here we've got liquid water going to hydrogen gas and oxygen gas. You can see hydrogen gas and oxygen gas on different sides of these two equations. So if we were to add them together, would cancel out those two hydrogens, cancel out the oxygens, and the overall equation would be liquid water going straight to gaseous water, the evaporation. All we've done is add those two equations together, so to find the overall enthalpy change, we can just add the two enthalpy changes together. give us 80 kilojoules per mole. In example 2, we can see carbon reacting with oxygen gas to give carbon dioxide gas, and you've got carbon dioxide giving us carbon monoxide and oxygen. We've got one carbon dioxide as a reactant there, and we've got a carbon dioxide as a product there, which will cancel each other out if we add them together. Then we've got half an oxygen there as a product, which will cancel with half of this, half of the reactant when adding together. And it's going to give us half an oxygen gas remaining. Add them together, we'll get carbon plus half oxygen gas to carbon dioxide gas. So all we did was add the two equations together here, and so all we would do to find the overall enthalpy change would be to add the two enthalpy changes together, giving us minus 111 kilojoules per mole. Many times you'll need to manipulate the equations before you can add them together to reach your target equation. 1. If an equation is written in reverse, the sign of the delta H changes. So here you've got carbon reacting with oxygen gas to give carbon dioxide gas. The exact opposite reaction would be carbon dioxide gas, giving us carbon and oxygen gas. So you just multiply the enthalpy by minus 1. Reverse and then multiply by minus 1. And so we're going to get plus 393 kilojoules per mole. If the coefficients of an equation are multiplied by some factor, then the delta H is also multiplied by the same factor. So here we've got ammonia gas giving us half nitrogen and 3/2 hydrogen gas. And we want to change that to get nice round numbers. So we're going to multiply the whole thing by 2. So equation multiplied by 2. So the enthalpy needs to be multiplied by 2, which will give us 92. Algebraic version, example 1. Enthalpy of neutralization of solid sodium hydroxide. The target reaction, the thing we're looking for, is sodium hydroxide solid plus hydrochloric acid aqueous, giving us sodium chloride aqueous and water. The component reactions are sodium hydroxide solid going to sodium hydroxide aqueous, so the enthalpy of solution. And we've got sodium hydroxide with hydrochloric acid. We've got a neutralization equation there, with the base is already in the aqueous solution. So we're going to look for a way to add the component reactions together to give the target. Equation 1, we're going to leave it as it is, because you can see the thing we want to get rid of is the sodium hydroxide. We've got 1 here, sodium hydroxide aqueous, and we've got 1, that's the product, and we've got 1 as a reactant here. So we don't need to change this. And we know that the enthalpy change is minus 43 kilojoules per mole, because it tells us just here. And equation 2, again, we just need one of these to cancel that. And this is a reactant, that's the product, so it's already in the right place. We don't need to switch around. We don't need to change the coefficient. So we can add them together, cancel sodium hydroxides to get sodium hydroxide solid plus HCl aqueous. And then we can simply add the enthalpies together. The third one is a bit more tricky. The enthalpy formation of ethene. We've got carbon solid with hydrogen gas giving us ethene gas. The component reactions here, we've got carbon solid plus oxygen gas to carbon dioxide. We've got hydrogen gas to half oxygen gas giving us liquid water. We've got ethene plus oxygen giving us carbon dioxide and water. We need to look for a way to add component reactions together to give a target. So we've got ethene on this side as a reactant. We also want it as a product, so we're definitely going to have to reverse this one. Over here we've got the hydrogen gas on the reactant side, so this is probably the right way around, but you see there's only 1 here, or 1, 2, so probably multiplying this by 2. And this one, we've got carbon on the right side, and got 1, so we're probably going to multiply it by 2. Let's have a look. So equation 1, let's try multiplying by 2, and we get the correct amount of carbons here that we're looking for. So we need to multiply the enthalpy by 2. Equation 2 multiplied by 2, that gives us the right amount of hydrogens. So we need to multiply the enthalpy by 2. And finally, we'll need to reverse this thing, and we don't need to multiply by any coefficients because we've got the right amount of ethane gas here. So let's just reverse it. And you can see now, we can just check our cancelling out. We've got carbon dioxide there cancelling. We've got the water cancelling with the water. And we've got 1, 2, 3 oxygens as reactants. 3 oxygens as products, which all cancel out. Add those all together, we'll get what we're looking for, which is fantastic. Now we need to add those enthalpies up, and it gives us plus 58 kilojoules. Okay, let's have one more go at this. Example 3, conversion of oxygen to ozone. We've got 3 oxygen molecules giving us 2 ozone molecules, both gaseous. We don't know what the enthalpy change is, so we can use these component reactants. Let's look for a way to add the component reactants together. We can see here that we've got oxygen on the wrong side here, so this is probably going to be minus. And we've got 1 here, but we want 3, so it's going to be probably times minus 3. And this one here, we've got ozone on the wrong side again, so this is going to be another minus, and there's only 1 here, but we want 2, so we're going to reverse this. It'll be minus 2. So equation 1 multiplied by minus 3 will give us 6 carbon monoxides plus 3 oxygen gases, and 6 carbon dioxide gases. Now let's multiply that enthalpy change by minus 3. Equation 2 multiplied by minus 2, so reverse the thing and multiply the coefficients by 2. Then we need to multiply the enthalpy by minus 2. We'll cancel out the carbon monoxides and add and cancel out the oxygens, the carbon dioxide, sorry. And it gives us the oxygen gas going to ozone. Now we can add those enthalpies together to get the overall enthalpy change. Okay, constructing enthalpy cycles is another way of looking at these things. When constructing an enthalpy cycle for the conversion of oxygen to ozone, what we'd do, we've got this target equation that we know of, and we've just looked at these 2 component reactants. An enthalpy cycle for this one would be as follows. We've got oxygen, and we want to take it to ozone. So if we want to go, we know that we can convert oxygen to carbon dioxide, because here we've got oxygen, a reverse would be to carbon dioxide, and we know that ozone can go to carbon dioxide, ozone to carbon dioxide. So we've got an enthalpy cycle. Oxygen to carbon dioxide is minus H1 because we're going the other way, and we can see it's 3 compared to 1, so it's going to be minus 3 H1. Ozone going to carbon dioxide, ozone to carbon dioxide is going to be plus this one, so we don't change the sign, but we do need 2 of them, so it's going to be 2 H2. And we know that we know that this here, this enthalpy change, delta H1, is going to equal delta HR plus delta H2. So let's write that down. We've got minus 3 delta H1 equals delta HR plus 2 delta H2. Stick in the numbers and you can find out what delta HR is. Another way of doing this is we know that oxygen gas go to carbon dioxide gas because that's what we used over here, but also carbon dioxide goes to ozone. Carbon dioxide here goes to ozone. So we could have put in minus 2 H2 going this way, but we need twice the amount. And then again, we know that this overall reaction is the same as the enthalpy change is the same as the enthalpy change going here to here. And so we could write it out as delta HR equals delta H1 times 3 plus delta H2 times minus 2, add them together to give us the overall enthalpy change. Splendid.